to ESE Electronics. This is a mock test of digital electronics subject. So you'll be getting the questions from digital electronics from various areas of digital electronics. I've tried to include the question. So if you're preparing for any competitive examination of electronics like AFCAT exams or ISRO exam or any competitive examination for that matter of electronics, you can attempt the mock test and you'll be getting to know that how much knowledge or how much you're good enough in this subject. And if you like the questions, please don't forget to like, share and subscribe. And also you can find the notes of this video in the description box. Now let's see the 10 questions. So this is a mock test for digital electronics. If you're preparing for any competitive examination of electronics, you can attempt this digital electronics mock test. It will be very useful for you. Now we are going to see the solutions. The first question is, you can see the question on board. The expression for absorption law is given by dash. So from the various options given, the first option is actually giving you the absorption law. Now absorption law means it is actually absorbing of some variables. Here the first option is a plus ab equal to a. Now a plus ab means you can take an a common, it will be 1 plus b, and this 1 plus b will be equal to 1 plus any term or any variable will be equal to 1 only. So a into 1, that is a. Now here you can see in this expression there is a b variable, but in the output expression or the simplified version doesn't have a b. So it is absorbing of the b variable. So the correct answer for the first question is option A. A plus AB equal to A is actually a statement corresponding to absorption law or the expression of absorption law. Now if you see the option D is A plus B is equal to B plus A. This is commutative law. Okay, so if the question is what is expression giving commutative law, means you have to select this option. But the question here is asking associative law, and hence the correct answer is A. A plus AB equal to A. Why? Because it is absorbing a variable B. It is not in the resultant expression. Okay. So correct answer for the first question is option A. Moving on to the second question. Now the question is from number systems. So I've tried to include variety of questions from various topics. The first question, so the second question is the representation of octal number 532.2 to the base 8 in decimal. That is, you have to convert this number in octal to decimal format. How to convert a number from octal to decimal is by multiplying these numbers with the powers of 8. Okay, I'll write the octal number once again. It is 532.2. So the numbers I'll write 5, 3, 2 and 2. So I'm going to write the position values 0, 1 and 2. Here it is. Since it is after the decimal, it is minus 1. Okay. Now represent these position values as powers of 8. 8 raised to 0, 8 raised to 1, 8 square. Now multiply with the corresponding number. So it will be 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to minus 1. Okay, so this will be the result, and the sum of this expression will be your corresponding decimal number, and that will be 346.25 to the base of 10. Since it is a decimal number, it is to the base of 10. Okay, that is 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to minus 1. Now why we are taking minus 1 is because it is after the decimal. So after the decimal, it will be minus 1. The position values will be minus 1, minus 2, minus 3. Likewise, it will go on. Okay. So the answer coming here is option A, which is 346.25 to the base of 10. Moving on to the third question. So digital electronics is actually one of the very important subjects. There's a lot of weightage for this subject in all competitive examinations. So try to give maximum importance to digital electronics, analog electronics, these subjects. So third question is the expression, I'll write the expression for you. Expression y equal to AB plus BC plus AC shows the dash operation. So expression is y equal to AB plus BC plus AC. And this shows dash operation. The options are A, XOR. Is this XOR operation? No, it is not XOR operation. B, SOP. SOP means sum of products. Sum of product. Is it sum of product? Yes, there are product terms and the product terms are being summed. It is a sum of product expression. Now the other options are option C, POS. POS means product of sum. So is this the products of sum? No. The products of sum will be like this. A plus B into B plus C into A plus C. So this is a POS expression. But this is not POS. This is SOP. Okay. Now the last option is NOR. No, this is also not NOR expression. Correct answer is option B. SOP is the correct answer for this question. Okay, so these terms are actually product of some terms. Sorry, these are the sum of the product terms, SOP. Sum of products. Okay, correct answer is option B. Fourth question. Fourth question is from CMOS. CMOS behaves as A or AND dash. That is, CMOS behaves as a dash. A adder, B subtractor, C inverter, D comparator. Very simple question. If you know the basic structure of CMOS. So CMOS is having a pull-up logic and a pull-down logic. We'll be realizing this pull-up using a PMOS. Pull-down is realized using NMOS. You connect these two bases and apply your input. And whatever input you apply to this CMOS input side, you will get the complement of it. That is, consider you are applying a variable A. You will be getting output complemented. So this is a basic working of a CMOS or a complementary metal oxide semiconductor logic. This is a CMOS logic. Okay. So you will be getting the inverted version. So this is nothing but a CMOS. A basic CMOS is a inverter. So the correct answer is C, inverter. Okay, so here there is VCC. I hope you can see it. So this is VCC, okay, or VDD. It is a high logic. This is the ground. Okay, this is ground. So this is a basic inverter. So a basic CMOS logic or a basic CMOS circuit is nothing but an inverter. Okay, correct answer is option C. Moving on to the fifth question. In 1 to 4 demultiplexer, how many select lines are required? So the question is from demultiplexers. The multiplexer, demultiplexer, this area is also very important. I'm going to draw the structure of a 1:4 demultiplexer or 1/4. So a 1/4 demultiplexer consists of one input. This is nothing but input bar output. Okay. And 4 outputs, demux. Now a demux and a mux, that is demultiplexer and multiplexers, have select lines. Okay, so if there is 4 select lines means it has, if it has 4 output lines means it has 2 select lines. Okay, so the concept is if there are n select lines, then output is 2 raised to n. Okay, since there is 4 4 we can write is 2 square, right? So the n value is 2. So number of select lines is equal to 2. Okay, so these are the 2 select lines. I hope the concept is clear. So we are discussing about a demultiplexer. Demultiplexer means it will be, that is, multiplexer combines, and in the case of demultiplexer it decombines. Okay, so there will be more output lines and less input lines. So since it is 1 to 4 or 1 to 4 demux, there is 1 input line and 4 output lines. Okay, now if there are 2 raised to n output lines, then n is the number of select lines. So here 2 raised to n is 4. Now we can write 4 as 2 square. So n is 2 here. So number of select lines is 2. Correct answer is option A, which is 2. So this is the logic which you have to apply for any demultiplexer. In order to find the number of select lines or number of output lines, you can use this logic. Okay, correct answer here is option A, which is 2 is the correct answer. Moving on to the next question, which is the 6th question. Yeah, 6th question is from flip-flops, and it is from JK flip-flop section. How is the JK flip-flop made to toggle? Now, if in order to answer this question, you should be familiar with the truth table of a JK flip-flop. We have done a very detailed video on the flip-flops. It is in the digital electronics playlist. You can watch it for your reference. Okay. So here we want to toggle JK flip-flop, and the truth table of JK is like this. There is a J, there is a K, and there is a next state Qn plus 1. Okay. And for various combinations, for 0, 0, 0, 1, 1, 0 and 1, 1, the output is like this. For 0, 0, it is the previous state itself. For 0, 1, it is 0. 1, 0, it is 1. And for 1, 1, it is Qn bar. Now, we all know that JK flip-flop is actually designed to overcome one of the problems or demerits of SR, which was, for the case of SR flip-flop, the 1, 1 state was not defined. But in the case of JK, we have overcome that problem or demerit by making this a toggled state. Okay. So in order to get a toggled condition of JK, we have to make J equal to 1, K equal to 1. Okay. Correct answer is option D. J equal to 1, K equal to 1 is the correct answer, which is option D. Moving on to the 7th question. Okay. 7th question is from shift registers. The question is a small numerical question. With a 200 kilohertz clock frequency, 8 bits can be serially entered into a shift register in dash. The question is regarding time. Okay. So the frequency F is equal to 200 kilohertz. Okay. This is the frequency. Now, we are designing a serial shift register. So, if for the case of a serial shift register, if the bits are entering serially, means 1 bit at a time or 1 bit in one clock period, right? So, what is the time period? The question is like that. Okay. Now, if the frequency is this, what is the time period? Time period T equal to 1 by 200 kilohertz, which is nothing but 5 microseconds. Okay. So 200 kilo means 5 microseconds it is. Now this is the time period. The question is not what is the time period. The question is how much time is taking for 8 bits to enter. So if 1 bit is taking this much time, we are going for a serial in shift register. Serial in parallel out or serial in serial out, whatever it is a serial input. Okay. So if the bits are entered serially, means every bit will take this much of time. So 8 bits means 8 into 5. That is 40 microseconds will be the time taken. I'll read out the question once again. 8 bits can be serially entered, means every bit is entering in one clock period. One clock period for 1 bit. Likewise, okay. So The total time will be 8 bits. I mean, for 8 bits, 8 into 5, which is 40 microseconds. Correct answer coming is option B, which is 40 microseconds. Okay. Moving on to the 8th question. The question is from Multivibrators. We have done a very detailed and very easy to understandable video on multivibrators. So, a stable multivibrator is dash in any state. This question is asking the condition, the state of the multivibrator. So, a stable multivibrator is dash in any state. A, stable. B, unstable. C, saturated. D, both stable and unstable and saturated. Very simple question. The name itself is stating that this multivibrator is stable. Means it doesn't have a stable state. It is just keep on changing its state. It is not getting stable or getting settled onto any state. So the answer is B, unstable. These type of questions also you can expect in order to just confuse you. Okay. You may be knowing the exact answer, but you may get confused while seeing the options. Okay. So a stable multivibrator is not having any state. So it doesn't have a stable state. So it is unstable. Okay. So a stable multivibrator is unstable in any state. Correct answer is option B, unstable. Now moving on to the 9th question. All logic operations can be obtained by means of dash. A, AND and NAND gate. No, we cannot realize all the logical operations using AND gate. But NAND gate, yes, it is possible. B, OR and NOR gate. Again, we cannot realize all the logical operations using only NOR gates or the combination of OR and NOR gates. C, OR and NOT gates. No, not again. D, NAND and NOR gates. Yes, it is possible to realize all logical operations using NAND and NOR gates. Actually, we have discussed about this question in a couple of videos. NAND gate and NOR gates are called universal gates. Okay, very commonly asked type of question also. Universal gates these are. And why they are called universal gates? Because we can realize any gates or any logic or everything using this NAND and NOR gates. Okay. So they are called universal gates and hence the answer is option D. NAND and NOR operations. Okay. The options is given as NAND and NOR operations. Yes, it is by doing the NAND and NOR operations, we can realize all logical operations. Okay. So correct answer is option D. Now, 10th question is a logical simplification, Boolean simplification. Simplify y equal to AB complement plus A complement plus B into C. This is a little bit difficult one. Not very difficult, but little bit difficult only. Okay. I'll write it down so that you can see it. Okay. Y equal to AB complement plus A complement plus B into C. Now while looking at the options are AB complement plus C, B AB plus AC, C A complement B plus AC complement, D AB plus A. Now how to get this form? We have a sum here and a product to that and again a product term here. Okay. Now in this bracket, what I'm going to do is I'm going to apply De Morgan's law. So if you apply A complement plus B and I'm going to apply double complement. Okay. So only then it get nullifies, right? So I'm going to apply double complement to this. We'll take the upper complement as it is and we'll perform De Morgan's in the lower complement and this expression. So A complement plus B the whole complement. It is equal to A plus B the whole complement is A complement, that will be A complement, again complement, it is A into B complement, it will be, right. So you'll get a term like A dot B complement. And again, there is a outer complement also. Okay, I'll put the complement as same notation. Okay, that is a plus b complement the whole complement, right? That is, if I take the bracket expression and put a double complement to it, you will get the expression like this: a dot b complement the whole complement. Now I'm going to substitute this expression like this. Okay, and I'll write it in the given expression. So I'll be getting a b complement. I've changed the complement signs. Okay, I'm going to give a bar. You can use either bar or the chords. Anyway, you can use. So a b complement plus a b complement the whole complement into c. Okay, so this is the expression. If you put a double complement and apply a De Morgan's to that, you will get a expression like this. Now I'm going to take this a b bar inside. That is, I'm going to distribute this plus sign. Okay, so it will be a b complement plus c into a b complement plus a b complement the whole complement. Right, I hope it is clear. I have just distributed this positive sign inside. So you can also write this like this, right? It's the plus and then a bracket, and I'm going to distribute this plus inside the bracket. So here there is a product term. So if you distribute the plus sign, it will be a b complement plus a b complement the whole complement. That term is here, and the next term is a b complement plus c, and then product of both those. Okay, so this will be your resultant expression. Now it is very easy. That is a b complement plus c, and this is 1 into 1. That is this. Okay, so a b complement plus c is your expression, and the correct answer is option A. I really hope you understood it. See, this type of questions needs practice. You need to know that in which place what logic to apply. So you have to practice it, only then you will get the trick. Otherwise, by solving any one question or two questions, you won't be able to get the trick or how to do these sort of problems. Okay, so how to identify that you have to apply De Morgan's is by practice only. Okay, so what I've done here is I've applied a De Morgan's, and before applying the De Morgan's, I've put a double complement. Double complementing means makes no effect. So just I have double complemented this bracket term, and I've given a De Morgan's to the term, and one complement sign remains as it is. So that expression you are getting is a b complement the whole complement into c again. Then the next thing I've done is I've distributed this positive sign inside the bracket. So I'll get two terms and then a product of that two terms. So a b complement plus c into a b complement the whole complement plus this term. Okay, so this term is 1, this term you will get as, that is the answer. Okay, a b complement plus c is your answer. So correct answer is option A. Okay, so these are the 10 questions which I will include in this video. So in this week, we will be doing the mock test of all your core subjects. So if you're preparing for any competitive examination, GATE exams, AFCAT exams, or ISRO technical assistant exam, or any examination, you can attempt these subject mock tests so that you will get to know that what is your knowledge in the subject. So if you have to prepare more, or if you are good in the subject, you will be getting to know that. Okay. So I really hope that you found it useful. If yes, please do give it a thumbs up, and also share it with your friends who's preparing for any sort of competitive examinations. And if you want more videos, please do subscribe to the channel. Thanks for watching, and keep on watching.